Okay, so this is section 8.4 example 8.4.1, and here they give us three lines. What are they? L, M, and N. So they've got a line L, and it uses the points A equals -4, 3, 1, and B, the point 1, 1, 0, and M, that line, and it uses C equals 2, 0, 2, and D, -1, 3, 2, and then N uses the point E, 1, 4, 7, and F, -4, -3, -13. Okay, and they want to know if these lines intersect each other anywhere, and then if they do, what's their point of intersection. So, let's look at these two lines, and so what I have is for L, that I have a given X is equal to A, that position vector, plus T times B minus A. Okay, so I have that line. And then I also have this other, that a given X is equal to C plus some S. Now it's important that you don't use a T again because we want to keep track of the different variables, and we want T to equal S, but if we call them both T or both S, well, then they're inherently equal. So now this is D minus C. Now, they go through, they use the IJK notation. I think that's kind of a mess to do that. I'm going to just use the parameterized parametric equations and look at a x1, x2, and x3. So what I have, I need to get up here so I can see what A was. Let's just look at x, right? X is equal to a -4 plus T times B, so that'd be 1 minus a -4. And here we have X is equal to our C, the first component, so 2. And I should call it X1, I guess. And then 2 plus S times -1 minus 2. And so this would say we need to have -4, and what is that, 5? Yeah, so plus 5t has to be the same as 2 minus 3s. Okay, that's from the first component. And from our second component, x2, go back here, the middle component is 3 and 1. So 3 plus t times 1 minus 3. And this x2 over here for the C and D, those middle components are 0 and 3. So that'd be 0 plus s times 3 minus 0. And so we get that 3 times negative 2t has to be equal to 3s. Okay, 2 equations, 2 unknowns. We could solve that, but there's a third. And so we get x3, and the third components of a and b, we've got a 1 and then a 0. So this is 1 plus t 0 minus 1. And here x3 is our third component, our 2 and 2. And so we get 2 plus s times 2 minus 2. That we just get a 0. So we have here that 1 minus t is equal to 2. And so generally, now in this case, I can tell you exactly what t has to be, and then I could tell you what s has to be from either of these first two, either this one or this one, first two equations. You know, here I can tell you t, then I can get s, and then I can check it in the others. But in essence, what's happening, I've got 3 equations, 2 unknowns. I can write that in my matrix style. So if I do t first and then s, I have 5, negative 2, negative 1 for the t's. And then I have negative 3, 3, and 0 for the s's, so ts, and that has to equal, now, you know, here, oops, oh, I got to be careful there. I almost made a, now, it's kind of funny, I don't know that it would have mattered, but I almost made a, yes, I guess it would matter. I didn't take the negative of that when I brought it to the left, and I didn't take the negative of that when I brought it to the left. So actually, I had those backwards. That should be a negative 3 and a positive 3, and then a 0. And then bringing the 4, the negative 4 over there, I get 2 plus 4 is 6. Bring the 3 over, I get a negative 3. And on the last one, subtract 1 from both sides, and I get a negative 2. No, subtract 1 from both sides, I get a 1. Yeah, not good with numbers. Okay, so now the question is this system solvable? And I could you know, do my augmented system here, minus 2, minus 3, minus 1, 0, augmented with 6, negative 3, and 1. And when I row reduce that, that better go to something here with 0, 0, 0 on the bottom. Okay? Because, right, I only have two unknowns, and if I end up with a 1 here, this is an inconsistent system. So if I'm going to have an answer to this, I need it to go to a reduced matrix with all zeros in at least one row. And does it do that? I don't know. So now I'm going to kind of do this in a funky order because I see right there, if I add equation 2 here up to equation 1, or well, actually maybe add equation 1 to equation 2, you know, I'll have a 5, 3, 6, but just add, I get a 3, 0, and add, I get 3. And then the bottom is negative 1, 0, and 1. And so what I can do now is swap the first and second rows, so I get 3, 0, well, and divide by 3. So I'll do that all in one step, and I'll get 1, 0, 1, and 5, 3, 6, and negative 1, 0, 1. And now, oops, what I see is this is going to be an inconsistent system, because I have no way to get rid of that 3, but notice when I add the top row to the bottom row and rewrite my system, I have 5, 3, 6, and I'll get 0, 0, 1. Okay, so there's my problem, is this is inconsistent. Now I could put it into Sage and do all that, but notice, I can get rid of the 5 with the top one up there, this one, and so that'll get rid of the 5, but it won't do anything to the 3. And so this system is going to eventually reduce to 1, 0, 0, 0, 1, 0, 0, 0, 1, which again is inconsistent. So these two lines, L and M, do not intersect. Okay, they don't. L and M don't intersect. Okay, so we've got that. Now, according to them, however, what does intersect? L and N intersect. Okay, so if we look at L and N, so that they're saying M and N do not intersect, so we could go through that pairing and we would also get an inconsistent system, at least according to them. And so we'll do this a little bit quicker with L and N. Okay, so again, let's go back up here, and I'm going to write down my A and my B. Okay, so I have X equals. Now, here's A. Let me go back up here and get it again. Negative 4, 3, and 1. Negative 4, 3, and 1. And then that's plus T times B minus this, and B was 1, 1, 0. So I get 5, negative 2, and negative 1. If I look back here, hopefully that's, yes, 5, negative 2, negative 1, yay! Okay, and again, for N, here I'll have to go back and find E and F here. E 1, 4, 7, and negative 4, negative 3, negative 13. 1, 4, and 7. 1, 4, 7 plus S, and I think I said negative 3, negative 4, so negative 3 minus 1 is negative 4, negative 4 minus 4 is negative 8, and negative 13 minus 7 is negative 20. Now the interesting part here is I could make all three of those positive and still just leave it as an S, because S could be negative or positive. So again, I thought that was what, negative 3, negative 4, negative 13. Let me go check that. Oh, other way around. -4, -3, -13. So -4 minus 1 is -5, and then a -7 here. So that wouldn't have been pretty. Okay, so we have this, and so if they intersect, we should be able to find an x where these are equal, or in other words, I should be able to find a t times 5, -2, 1, minus an s, -5, -7, -20, plus a -4, 3, 1, and minus the 1, minus the 4, minus the 7. So I just brought this stuff over to the left side, so I made it all negative, and we should get that this equals 0, 0, 0. Okay, and actually I probably should have left this over on the right hand side, but so we have our 5, oops, and I think I had a typo, right? Yep, -1, or a righto or something like that. -2, -1. This is a minus, right? So I've got 5, 7, 20 all times TS, and that is supposed to equal a 5. Like I said, I should have left it on the right hand side, a 1, and a 6. All right. So again, I would just look at my augmented matrix, -2, 7, 1, -1, 20, and 6, and hope that I can reduce this thing. Well, certainly I'll divide through the top by 5, and so I get that, and now I'm going to add 2 of the top to the second row, so I get a 0 there, and I'll get a 9 and a 3, and I'll add 1 of the top to the bottom row, so I'll get a 0 and a 21 and a 7. That's looking good. Okay. So 1, 1, 1, 0, 1, and 1/3, dividing through by the 9. And so now if I multiply the middle by -21 and add, I'll get 0, 0, and -21 times 1/3 is -7, and so I'll get 0. Awesome. And now if I just subtract the second row from the first, I get 1, 0, and 2/3, 0, 1, 1/3, 0, 0, 0. And so this tells me T equals 2/3, S equals 1/3. And so now, oops, I'll tell you, I guess I'm either all thumbs or all palms or something. So now I can find that point, and I can either use S or T. So I go back here, and so I can either use T in this or S in this. I think I'm going to use that one. So T was 2/3, so -4, 3, and 1. Okay, so my X of intersection is -4, 3, and 1, plus 2/3 times 5, -2, and 1. 5, negative 2, and 1. And so that is negative 4 plus 10 thirds, 3 minus 4 thirds, and 1 plus 2 thirds. So if I got this all right, that's minus 12. So minus 2 thirds, 9 thirds, so that'd be 5 thirds, and 5 thirds is our point of intersection for those two. And I'm looking at the text. Negative 2 thirds, 5 thirds, oh, 1 third. Oh, gosh, I keep doing that. There, that should be a negative. And so this is minus 2 thirds. Keep dropping that negative on that thing. I don't know why. And so yes, I agree with them. That should be 1 third. So, okay, and that is our point of intersection. And again, we could check the lines L and no, we did L and N, M and N. Well, we're not going to do that, but let's take what happens with two parallel lines, right? So if a couple lines are parallel, so let's just look at, suppose I have one line, so L1 is equal to, we'll just go with 1, 2, 3, and then, whoops, and then plus some t times 4, 5, 6. Now L2, that is, say, 3, 2, 1 plus S 4, 5, 6. So now what happens with that? Well, we get 4, 5, 6, 4, 5, 6 minus on those when we bring them over to the other side, times our T and S is equal to, now I've got this on the right hand side, that has to come over from the left hand side, so I subtract and I'll get a 2, a 0, and a negative 2. And so pretty quickly I see that what I would have on this is, in my augmented system, 1, negative 1, 0, 0, 0, 0. Okay, I know I get that. Now here I divided that 2 by 4, so I'd get a half. Divided 0 by 5 to get 0, but then to knock this thing out I subtracted, so I would get a negative half, I'm pretty sure. And again, similarly, I would start here with a negative 1 third, and I would subtract that 1 half, so that would be negative 1 sixth, I think. Oh wait, no, subtract. I have negative 1 third, subtract a half, so negative 5 sixths, I believe. And so you see, very inconsistent. They don't intersect. Well, what was the problem? Well, I had the same direction, but a different starting point that was not on the other one's line. Now, so just to show, though, that this can all work out, suppose I take a starting point like 5, 7, 9 for my other one. Okay, so now I have L1, and that's still my 1, 2, 3 plus T times 4, 5, 6. But now a definite point on this line is 5, 7, 9. So suppose I take this X and go 5, 7, 9 and plus S times that same direction vector, 4, 5, 6. I could even make it negative if I wanted. or I could make it 8, 10, 12. It would still be the same direction. But now, when I do this, I have that same augmented matrix that I'm starting with on the left-hand side. But on the right-hand side now, I have 5 minus 1 is 4, 7 minus 2 is 5, and 9 minus 3 is 6. And so you see what happens is this would go to 1, minus 1, 1, and these others would all become zeros. So this is consistent, and we see that in this case it's saying t minus s is equal to 1. Okay, from our augmented system. And so that says, oh, choose t to be equal to 1 minus s. So there are infinite number of possibilities. Why? Well, because these are the same line. They intersect everywhere. And notice if we let t be 1 minus s, then we get what? We get our 1, 2, 3 plus 1 minus s times 4, 5, 6. But that I can write as, I'll get a plus 4, so I'll get 5, 7, 9. And, oh, minus s plus s was t minus s, so that's plus s, and so then plus s times 4, 5, 6. Oh, yeah, same line. Okay, so if they are the same line, we'll be able to see that by a relationship, something like that. Okay, so that is a very expanded version of example 8.41.